Hi everyone, welcome back. In this video I'm going to be talking about invertible functions, so functions that we say has an idea of an inverse. And so before being super concrete about what that is, the most important concept with invertible functions is that invertibility will guarantee us the preservation or conservation of information. And I alluded to this idea when I talked about injectivity of functions, and I'm hoping my argument there was pretty convincing. But if not, I'm going to give you a simple example that you guys are already familiar with. So if you think about the question, if I have a real number x, so I say x is in the reals, and I say I know that x squared is equal to 9, and I ask you, okay, well, what is x? Like a specific value of x. You might start out by telling me, okay, well, this means that x is plus or minus 3. And that's fine, but this isn't what I want. I want one value for x, a specific value. And that's something that you can't guarantee me. Because if all you know is that x is a real number and that its square is 9, you can never know what x is. You can never know whether it's positive 3 or negative 3. And so if you think about this sort of transformation from going to x squared, there's this information that's lost. So we know that both x and minus x will map to the same thing. And so the information that's contained within the sign of x is lost when going to x squared. So we lost information on the sign. Okay. And this is actually pretty important in other contexts. For example, solving equations. So we saw a sort of simple equation here, but if you always wondered, how did miscellaneous solutions come about? You would solve these kinds of equations. So let me give an example. I can't guarantee that this has a nice, integer solution, but I'm just coming up with something on the spot. So what would you do here? You would square both sides of this equation, right? You would get some quadratic equation, and then you would solve that, and then you would see, okay, there are two solutions for x, but potentially one of them doesn't actually work because you put it into here and you get a negative, and that's not good. Or maybe you get a positive, but this side just doesn't match this side. So you usually get one miscellaneous solution. Now, why does that happen? Well, the thing is, if I say that x satisfies this equation, it's perfectly fine to say then that x satisfying this equation implies that x also satisfies this equation. Right, and we can expand this out to get, just do some math here, 4x squared plus 16x plus 16. Right. So we know that x will satisfy this equation, but the whole point of solving an equation through something like this, and actually the ways that you guys are familiar with solving equations in general, is that you establish this sort of chain of implications where we're going to get x equals blank or blank. And then the idea is that, oh, we can also go back. And what that's saying then is that here are my solutions for x. If I can go back in my implications, then this means that if x is equal to one of these two values, then it will satisfy this. The problem is, though, is that as we saw, when you square a number, you can't necessarily go back because you don't know which number you came from. So this step here, you can't actually go back. And that's why you get these miscellaneous solutions, because there isn't necessarily this backwards implication of x being equal to a certain value, then implying that the original equation is true. And what does that all stem from? It stems from the fact that this function x squared is not invertible. You can't go back in a sensible way to the domain. The information is not preserved. Okay, what exactly makes x squared not invertible? So our function is f from the reals to the reals, and what it does is it takes x to x squared. Okay? And now we can graph this, right? And we get something that looks like this, more or less. An issue we see is what I would like to call the horizontal line test. I think that's probably a term people use in general. The horizontal line test, and you have this line intersecting the graph twice. What it means is that you have two distinct elements of the domain that have the same value in the range. And so this condition of injectivity that we had before, which is that f of x equals f of y, implies x equals y. This is not true for the function x squared, because I can have x and negative x that both map to x squared. So this function is not injective. And what happens when you have a function that's non-injective is that if you know a specific value, right, you cannot deterministically go back to the element, oh, damn it, go back to the element of the domain that it came from. Right, you have to make a choice here, and that's not something that we like, because that means we lost a bit of information, because if we had that information, we would be able to tell where we came from. Not having injectivity is an issue, right? It's telling us that we can't go back through the function. Another thing is not having surjectivity, which is saying that there are values in the range that are not mapped to. And we can kind of see that here also with our function x squared, because there are no real numbers whose squares are negative. If I have, x squared equals, let's call this -3, then I can't tell you what x is if I'm saying x is a real number. So now I just can't go back at all. And so this is also an issue in solving equations, because you have something like this, then you just don't get an answer. I then want to bring up another example that I think more clearly demonstrates how invertibility is related to preservation of information. So if we think about a physical body, this is like an object that takes up space, and it's made up of particles and all that. We can think about it as a subset of three-dimensional space. So I have sort of an amorphous blob. There we go. This thing we can say is actually a subset of R3, the three-dimensional space. And potentially, this thing can undergo a deformation, right? So usually we like to label deformations with the Greek letter phi. And this thing can change shape in some way. Let's say it becomes something like this. What we'd like to say, in physics, if there's only really like physical, not chemical changes going on, is that this sort of information about where each particle moves to under the deformation should be conserved. Or we can say, maybe better, that the information about the particles that we have in here, so we have particle information here, should be preserved through this deformation, where we have also particle information here. We can think about that as being able to say, if I know the particle here in this original body before the transformation, then I know where it will go to. And also, if I know where this deformed particle is, so a particle in the deformed body, then I also know where it came from. The idea then is that if you consider all of the particles in the original body, so let me call this B, let me call this B prime. So if I consider all the particles in B, I should be able to know where they all move to in B prime. And then at the same time, I should be able to know where all the particles in B prime came from. And you can, if you imagine this sort of visual continuous deformation, then the visual idea of this is being able to go through the deformation and then also go back, if you can kind of play that animation in your head. Okay, well, where could this potentially get messed up? Well, let's say we have two distinct particles in B, and they both deform to the same location in B prime, so that they somehow merge to become one particle. Well, then you can't really play back the deformation, because where does this one go to? Does it sort of like branch out? Something weird is going on. So maybe there's some sort of chemical reaction that combines these two particles in B to become one, but it's not really clear what's going on. Additionally, okay, so let me just finish off by saying that in this example, the deformation phi is not injective, and this creates the issue of destroying some particle information, because we had information about two particles, right? And suddenly it's just become one. Okay? All right. An additional issue that could happen is that maybe this deformation only maps the original body B to some subset of the new body B prime. So maybe only in this part we have the image of phi, and then here we just somehow have these new particles. Okay, so basically what I'm saying here is that phi, in this example, phi is not surjective, and the question is, well, where did the particles in this new region come from? They certainly didn't come from B, because then they could be described by this deformation phi, right? They would be elements of the image of phi. So we now have no information regarding this whole region of particles and where they came from. So somehow just new information has been added and we don't know where it came from. What this physically means is that the body B and its evolution through time is an open system, right? It's just receiving information externally. And that's pretty significant. And when we want to consider, a system of like the whole universe, that is essentially by definition a closed system. And so we shouldn't just get new information influxed into the universe, and it also shouldn't just disappear and be destroyed from the universe. So that's why a fundamental principle of physics is the conservation of information. Okay, and what is my point with this example here? Well, what I was demonstrating is that the two issues that could violate this principle are the lack of injectivity of phi and the lack of surjectivity of phi. If you remember, we said that if a function is both injective and surjective, we call it bijective, right? So what this means then is that if phi is not bijective, then information is not conserved. Okay, I've cut the second half of my original recording because the video was far too long. So I'm going to summarize the important points of this video now. So we saw that if a function phi is not bijective, then information is not conserved, right? So we can say information is conserved. That must imply that our function is bijective. Wow, my handwriting is getting terrible. Okay. So now I want to say that information being conserved, when we said that, what we mean is that we have a way to go back through the function in a well-defined way. And because when that is true, then information is neither destroyed nor just randomly added in externally. And so what that means then, to have a well-defined sense of inversely mapping through our function phi, is that if our function maps from this first set into the second set, then we can have an inverse mapping that takes our values back to where they came from in the domain in a way that is also a function. That's what I mean when I say that this is well defined, right? And the fact that it is well defined is key to the idea of information conservation. So if you remember what our rules were for a mapping to be well defined and thus be a function, our first one was that it must map every element of its domain, right? So phi inverse maps every element, and let's call this b prime just to be consistent with what I was doing before. Okay, so when does this happen? Well, phi inverse only maps values of phi back to where they came from, right? So if phi inverse maps every element in b prime, that means that every element in b prime is a value of phi. And this is exactly what it means for phi to be surjective. Okay, what about our next rule? Well, our next rule for well-definedness is that phi inverse must be single-valued. In other words, it cannot be multi-valued. Well, what does it mean for phi inverse to be single-valued? That means that when I take this value of phi and send it back to where it came from the domain, if it's single-valued, that means that it only came from one element of the domain, which means that unique inputs map to unique outputs. And this is the conceptual way of saying that phi is injective. Okay, so overall, what we've done is link bijectivity to conservation of information. We also linked conservation of information to invertibility. And now we've linked invertibility to bijectivity, because we see that each principle of well-definedness for the inverse map exactly corresponds to either the surjectivity or injectivity of phi. All right? So our main conclusion from this video is that phi inverse exists. So this is an inverse function, phi inverse. If and only if the function phi is bijective. Hopefully that is clear to you conceptually from this whole video. And from now on, we will use these terms, invertibility and bijectivity, interchangeably, because they are exactly equivalent. Okay? All right. So the video about functions, the first one, introducing functions, and this video are really the main two that I want you to see before we meet in person on Monday. And our first lecture will be about symmetry and groups. And I'm very excited because these are my favorite topics in both math and physics. It's really one of the most important topics in physics, and I'm glad it's going to be the first one that I get to present to you. All right, I'm really excited to see you guys on Monday, and that's exactly where I'll see you. All right, bye.